Now we're going to look at the relative min and max. Okay. Sometimes these are called the local min or max, as opposed to the global min or max, or absolute min and max. So basically, a function has a relative min or max at x equals c if for all the x in some open interval containing c, you have that f of c is less than all the other values in the interval. That'll give you a minimum. Or f of c is greater than all the other values in the interval. Okay? And so intuitively, when you look at the graph, so here's a kind of a strange looking graph, but when you look at the graph, the relative mins and maxes are like the peaks of the graph or the valleys. It's where the graph kind of gets to its highest point, turns around, to its lowest point, turns around. And even here, where it kind of makes a sharp turn, but it turns around. So, I don't know, I'll call this C1. And this is a relative min, or this is a relative max. And the point here is you can find an open interval containing C so that all the x values in that interval are smaller than f of c. Okay, this is the largest function value in some interval containing c. And in this case, this would be a local min. Okay, it's not the minimum value over the entire function, but there is an interval, an open interval containing c where it's f of c plus 1, or f of c1, let's call it f of c2, where that is actually the lowest value in that interval. And this is another place, C3. And again, this is a max. There's an open interval where all these x values are less than the value at that point. And so that is, in this case, a local maximum. Okay, so if we looked at this entire thing, these are some interesting things. So this endpoint is actually a minimum value. It's actually the absolute minimum value over the whole function from a to b. It's the absolute minimum value. Okay, this is a local minimum value, or local maximum value. It's not the absolute maximum value. This is a local minimum value. It's not the absolute minimum value. This is a local maximum value, but it's also the absolute maximum value over the interval a to b. It doesn't get any higher than that. That's the highest value over that whole interval. And this would be you could think of this as a local minimum value, okay, at the endpoints. If you wanted to, but normally we just think of those as the endpoints. So, so what can we tell? Where do these relative extrema occur? Well, like I mentioned earlier, if your derivative is equal to 0, f prime of c1 here is equal to 0. So if you have a horizontal tangent line, that's where the graph makes its turn, right? It got positive tangent lines, they get smaller and smaller. At that point, it's 0, and then on this other side, they're negative, right? And so if it makes a turn like that, if the derivative is equal to 0, that's if you have a relative extrema here, that's going to be a point where this derivative is 0. Same here. But also, and this is why I was stalling over there, it doesn't have to be that the derivative is 0. It could also be, at this point, f of c3. It's not, this derivative is not 0, but this is undefined. And when it's undefined, it can make a turnaround as well. Okay? So either you get a smooth turnaround or a sharp turnaround. But the point here is those local minimum and maximum values are going to occur where either the derivative is 0 or the derivative is undefined. Okay? And I drew a horizontal tangent line. Well, you could draw all kinds of tangent lines here, right? So there is no tangent line to the graph at that point where it makes a sharp turn. So let's actually define this. Let's call a critical point here. A critical point of a function is an x value, x of c, such that either the derivative at c is equal to 0 or the derivative is undefined, just like I said earlier. So if the derivative is equal to 0 at c or it's undefined at c, then c is a critical point. Okay? And so now what we have here is a relative extrema value theorem. That's what I'm calling it. So we got another theorem here, and it basically says this, and you have to be real careful about this, and that this is true about a lot of these theorems. You have to pay attention to the conditions. So what this says here is if f of x has a relative min or max at x equals c, then x equals c, I should say, x equals c is a critical point of the function. So what this is saying here is if it has a relative min or max at a point, then that point is going to be a critical point. Notice it doesn't work the other way around, okay? Just because you have a critical point, just because x equals c is a critical point, doesn't mean that the function will necessarily have a relative min or a max there. So that's why these are the two classic examples here. So when you have a parabola like this, at this point the derivative is equal to 0. So the derivative of f at 0 would be, the derivative here, dy dx, is just 2x, right? And 2 times 0 is equal to 0. And that is a relative min, okay? So this is a critical point, and it is a min. But notice here, dy dx of x cubed is 3x squared. And then at that point, at 0, f prime of 0 would be 3 times 0 squared, which is 0. And so, in other words, this function flattens out here, but instead of going back up like a parabola, it's going down this way, right? And so this is neither a min or a max, even though that point is a critical point. The derivative is equal to 0, right? It's getting closer, it's flattening out, getting closer to 0. It is 0, but then what it's doing here is it's starting to get steeper, okay? Again, instead of this one, it's kind of flattening out here, and then it goes back up the other side, and it increases the other way. Okay? So, in other words, this makes a turnaround. This one kind of flattens out, but then kind of keeps on going. Okay? And so, what we get here is, if there is a relative extrema, it will occur at a critical point. Okay? So, if you want to find a relative extrema, find the critical points. Find either where the derivative is equal to 0 or the derivative is undefined. And at those points, that's where the relative extrema are going to occur, but it doesn't mean that it will occur. It doesn't mean that there will be a relative extrema. There could be, though, and so you have to investigate further to know if it is a relative extrema or not. Okay? And so, what I wanted to do is I wanted to go back to this example. This is that cubic equation where you had these points. This was like -3, 45 or something like that. And then this here was -3 something. Let's see if I can graph this. Again, x cubed minus 3x squared minus 2x plus 3, and then I'll do a standard window, and so there we get the function. And so if I do second calc, and then 1 for value. If I put in negative 3, then you see I get negative 45. This should be negative 45. And then if I put in a positive 3, then I get negative 3. So this is positive 3 and negative 3, right? Positive 3 and negative 3. Okay, so this is where the relative extrema are. We can see that from the graph. So these are critical points. So if we want to find exactly where these occur, what I can do is I can take the derivative, set the derivative equal to 0, and find when the derivative is equal to 0. And then I'll actually find where those relative extrema occur. Okay, so let's do that. If I take the derivative here, I'm going to get 3x squared minus 3x minus 2. Okay, so I get this function there for my derivative, and so now I set that equal to 0. I'm going to find where the derivative is equal to 0. And notice it is a quadratic equation, so there's going to be 2 roots to this, so the derivative will be 0 at 2 places, and you can see that that's where these are going to be. So solving this is actually going to find those relative extrema. So let's actually solve that, and I'm going to use the quadratic formula. So the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So this will be 3 plus or minus the square root of, this will be 9. Let's see, 9 plus 24. So this is 33 all over 6. So I'm going to get 2 solutions here. So 3 plus the square root of 33 divided by 6. And so one of my roots is 1.457 approximately. And then the other one is going to be divided by 6, and the other one is approximately negative 0.457. So not at all obvious, right? These are irrational numbers, okay? But let's look at our graph again. Here's our graph, and maybe I can zoom in here, and let's put in these numbers. So second calc, and if I put in the 1.457, and I do not get, I did not get this. I thought this was going to be the minimum value. So what did I do? We're going to have to go back. It's okay, I make a mistake. Then you'll feel good, right? You'll know that even your teacher makes a mistake, right? Let's see what I did wrong. So this would be 9. Oops. Let me look here. First, take the derivative, minus 3, and then this is minus 2. So the opposite of b, which would be positive 3, plus or minus 9, 9 minus 4 times 3 times negative 2. Yeah, I get 33, and then I have 6 on the bottom. Maybe I didn't put my equation in right. Yes, I put in my equation right. Oh, I know what I did wrong. Sorry. Okay, I see what I did wrong, and maybe you caught it right away. So when I take the derivative here, when I take bring down the 2, that should have been a 6x, not a 3x. So this should have been a 6x. That would have made this 6, right? It would have made this 6. And so now let's try it. So instead of this, I'm going to get 6 plus or minus. This will be 36 minus 4 times 3 times negative 2. So this would be square root of 60 all over 2 times 3 is 6. So let's I'm going to put this in then. I'm going to put 6 plus square root of 60 divided by 6. So I get 2.29, and with the minus I get approximately negative 0.29. So these should have been my roots, not what I got up above. And so now let's plug these in. I think I accidentally typed something there that I shouldn't have. So x cubed minus 3. Okay. So let's see what happens. Let me graph. And then let's put in my values here. Second, Calc. Put in the values. Now I'll put in 2.29. And I see that is the minimum value. And the minimum value there is like 5.303 or so. And then I can put in, that's the local minimum, by the way. The global minimum is at negative 3 at the end point. Now let me put in negative 0.29. And there I get the other, that's the maximum. It's like 3.303 or so. So this would be the minimum. Oops. This is local. That's actually, this probably should have been negative here. Local min, local max. And let me just put in 2.29 again. Yeah, negative 5.303. Okay, so here's overview then. The relative min and maxes are these points where the graph turns around, and they will occur at a critical point, and the critical points are either where the derivative is 0 or the derivative is undefined. And if you have a critical point, it may or may not be a relative min or max, but the relative min or max will occur at a critical point. So you find the critical points, and then you got to check to see if they're a relative min or max. Right now, you can use your graphing calculator to check to see if it's a relative min or max. But later on in the chapter, we're going to learn something called the first derivative test and the second derivative test. And there are techniques that you can use to determine whether or not the critical point is a min or a max. Okay? So that's the thing behind the relative min or max. So now we're going to put both of these together, and since in the first video we saw that a continuous function on a closed interval will contain an absolute min and an absolute max, then all you need to do is find the critical points that lie in the interval, and then you just test it at the critical points. You plug in the values at the critical points and at the end points, and then whichever value is the smallest will be the global minimum over the interval. Whichever value is the largest will be a global maximum over the interval. And so as far as a continuous function over a closed interval is concerned, we now have a way of finding the global min and max over that closed interval.